The transshipment model is an extension of the transportation model. Okay, and the typical example is this. The transportation model, you have a supply node, okay, and you are now able to move items from a supply junction to a demand junction. But then there's a transshipment node. Like from Okpongolo to 37, there is a transshipment node, which is Akramo. So that is where things happen, and then they distribute everything all across. So that is a transshipment mode there. There's nothing interesting to teach for your level. So, but there's a bit of detail for the master's level that MBA master's level that you can check. But the key important one that we want to look at is assignment model. That is critical. That is important. We're going to use the assignment tableau, okay, to also solve the assignment model. The assignment problem is a balanced transportation problem. Balanced already. When we say balanced, it means that the number that is being supplied is the same number that is being demanded. It's not like the transportation where you are supplying 100 and I'm demanding 300. No. This one, what you are supplying is exactly what I'm demanding. A typical example is when you're looking at projects, okay, you are assigning project to some people. Okay, so it doesn't matter the number of people that are applying for the project is the number of people who are being demanded for the project. A typical example again is a contract for bidders. So when people are bidding for contract, okay, the contract is one, the bidding is one. So you have the same number of people who are bidding the contract. Another example is a referees. Okay, in a typical match, football match, you have only one referee, one center referee for one game. So if you send all 20 referees to the game, it's not going to be useful. Okay, you just need one center referee for the game. Okay, when you are having a team of auditors, there's the same thing, one team of auditors for one company. You don't need to have this team of auditors, another team of, no, you have one team of auditors for one company. And this assignment problem is an M by M matrix, okay? And the best way to solve it is using the Kuhn's Hungarian method, okay, which we shall use now. First, let's define the Hungarian method. It says that if a number is added to or subtracted from all the entries of any one row or any column of the cost matrix, then an optimal assignment for the resulting cost matrices are also an optimal assignment for the original cost matrix. It's a theorem. It wouldn't make sense unless we go through it. Okay, so let's go through it a bit more. It was postulated by Harold W. Kuhn in the paper titled The Hungarian Method for the Assignment Problem, published in the Naval Research Logistics in 1955. It described a procedural analysis for developing the maximum weight perfect matching in a bipartite graph. The word Hungarian algorithm applies the above theorem to solve the assignment problem. Okay, and that's what we shall be doing here. So let's take a typical example of a situation. This is an Atlantic Coast Conference. Okay, and this coast conference is like you might call it like the Premier League. Okay, but this is a typical example of coast conference games. It's a games, and they normally play these games in the night. At a particular night, the conference office who manage the program, they want to assign 4 teams of officials. So if you have one group of officials, the numbers are 4. Another group of officials, the numbers are 4, and we are sending them to 4 different games in different towns. So I want you to look at this like the Premier League. You are sending one referee to each town. So Man United is going to play Chelsea. It's one game. And you are sending one center referee to that game. And they are also expecting one center referee for that game. They are not expecting 30 or 60. Now, the distances that are traveled by these officials, the goal is that the office want to minimize the total distance. So the total distance traveled by the officials, okay, the office want to minimize this. And the distance are in miles, okay, for each team of official. Okay, and we have the distances shown here. So the officials who are officials A, they have to travel to the game site. The distances they have to travel to get to Raleigh is 210. The distance they have to travel Atlanta, should they go for R, A, D, or C? Raleigh, Atlanta, Durham, or Clemson? Which one should they go for? This one is easy. Easy, but it's not simple. Which distance should they go for? We want the lower distance. Which should? Who can chat the answer there? Okay, so they go for the distance, which is 90. Okay, that's what someone might say, 90. But I want to look at officials. B, today will go for 90, C will go for 90, D will go for 90. So it appears that everybody will be going for the 90. That is what it appears that everybody will do. So it might be that the 90 might not be the best after all, because everybody would want that. So how do we now allocate them in such a way that the total, not just one person, but the total distances are minimized? How do we allocate them? Well, the first thing is to define the decision variable, okay, for this assignment problem. Okay, it's supposed to be assignment. Develop a network graph model, formulate a model, and what is the optimal solution for the officials and the games using the Hungarian method. So that's what we're going to do. How do you define the problem? Well, we let Xij be team of officials I to the game site J. Team of officials I to the game site A. That's what we have there. Team of officials I to the game site. And the officials are 1 A to D. And the game sites are R, A, D, C. So that's what you have there. Okay. Now, we are to develop a network graph model. Now, if you look at this, how many are the officials? 4. How many are the game sites? They are also 4. So if we are to draw the network graph model, the way you draw it is going to be just 4 by 4. Okay. If you look at the way we draw it normally, it's just going to be 4 by 4. So you take the first one, and then you have what? You have the first one, you have the second, you have the third, and then you have the fourth. And then if you do the other one too, it's the same approach. First, you have the second, you have the third, you have the fourth. So that's what you have there. Now, how do you allocate? Now, remember, it is the group of officials from A going to B. Now, if you look at the, okay, remember, it is A, B, C, D that have been used, going to Raleigh, Atlanta, Durham, Clemson. So we can write those terminologies in here. We can indicate the naming, the numbering right here. So you have this to be A, you have B, you have C, and then you have D. And then the names of the places, we have Raleigh, Atlanta. So I'm just going to use letters, Raleigh, Atlanta, okay? And then you have Durham, and then Clemson. So when I have a distance, okay, let me just use a different color here. When I have a distance that I want to actually show, I am showing a distance from this. No, I'm showing a distance from here going to this section, okay? And I'll call it XAR. Don't forget, XAR. Then I'll attach my distance to it, Okay. The next one will be XAA. The next one will be XAD. The next one will be XAC. And so if I were to attach the X's to them, that's the name. So this one is going to be XAR, XAA, XAD, XAC. Okay. Then you do the same thing. Okay. You do the same thing for the next group. So from A going to B going to R, you are from B going to A, you are from B going to D, and then you have B, and then you come and label them as well. Of course, that will be plenty, but you can understand what I'm trying to do. And then you come to this one to C going to A, come to C going to B, R and then A. You have come from C going to D. You have from C going to C, and then the last one you have from D going to A. You have from D going to A, first going to R, and then you have from D going to D, and then finally you have from D going to C. Okay. So obviously, how many decision variables are we going to have? We are going to have 16 decision variables. How many constraints are we going to have where to formulate the constraint? 8 constraints. Okay. And this is an assignment problem. Assignment problem. So if I were to write the decision variables, I just take the numbers, because remember, for each one, you have the data. Let me just show you. So for each one, you have the data. So these are the distances. So you attach the distances, you attach the distances, you attach the distances to each of them. And so when you're formulating the objective function, you formulate the objective function with the distances. Okay, and you multiply each distance by the decision variable, each distance, and that will give you a very long objective function. What about the constraint? Well, the constraint, you just have your decisions. Okay, so you just have, so the constraints are going to be something like, if you are having your constraint, it's going to be something like, if I were to talk about a constraint for this, okay, the first one, okay, the constraint for that, then I'm going to have the acts that are leaving it, which is what? XAR plus XAA plus XAD plus XAC equal to 1. Okay, equal to 1. And that will be the constraint for the first node. And then you do that 8 times for each one of them. Just look at the acts that are leaving it and the acts that are entering the other one. And that will give you the constraint. So when you do all of that, this is a constraint you're going to have. You're going to have this objective function, okay, where you're minimizing the distance. And you have all of these 18 decision variables, each multiplied by the distances. And then the constraint, I told you there are 8 of them. And you don't forget your non-negativity constraint. And the constraint, each one is equal to 1, just as we have indicated. If you do that perfectly, this is your formulation that you are going to have. Okay. Now, how do you perform the Hungarian method for this assignment problem? Now, first of all, this is a balanced assignment problem. Okay. Balanced because 1 is needed, 1 is expected, 1 is sent. First is to perform the row reduction by subtracting the minimum value in each row from all the rows. So when you take all the rows, for each row, you subtract the minimum value there. Okay. And then you perform the column reduction by subtracting the minimum value in each column, and then cross out the zeros using the minimum number of horizontal or vertical values. Now, if you are having fewer M lines, okay, if fewer M lines are required, the M is the number of rows and the columns. Okay, so if you need fewer of them, then you have to subtract the minimum ones that you have not crossed, okay, the values you haven't crossed from all other uncrossed values, and then add this same value to all cells where 2 lines meet. And then this algorithm is quite complex, but again, when we start applying it, you see that it's very simple. And then finally, if M lines are required, the Tableau has optimal solution. And M unique assignments can be made if fewer M lines are required. Then you repeat the process. Okay. So let's take those approach and then apply it to this Atlantic coast problem. Assignments are made to locations with the zeros in the opportunity cost table. Okay, note that. And then the optimal solutions occur when the number of independent unique items equal the number of rows or columns. So if the number of unique assignments is less than the number of rows or the number of columns, whichever one, use the line test where all zeros are crossed. And then the minimum uncrossed value is subtracted from all other uncrossed values and then added to the values where the two lines cross. So let's take this. Let's develop an opportunity cost table. This is what we know. We know this from the beginning. So there's no problem with these values that we have here. Let me just get a highlighter and then walk you through it. So what is the first thing to do? Well, oops. So you look out for the ones that have zeros, the columns that have zeros, that have the lowest distance, the lowest distance, and then you cross them. Okay, you subtract and then you cross them. So let's take the first one. If you look at this column, Atlanta, it has 90. Okay, it has 90. So on that row, you are going to subtract 90 from all the others. So if you subtract 90 from Atlanta, you get 0 because it has the lowest distance. Then you subtract 90 from Durham. That will give you what? 90. Then you subtract 90 from 210. That will give you what? 120. You can check it. And then you subtract 90 from 160, and that will give you 70. So that is for this. Okay. And then you do the same thing for the next one. The next one, the lowest column, sorry, the lowest row, the distance that you see is 70. So you subtract 70 from itself, you get 0. You subtract 70 from 100, you get 30, that is here. You subtract 70 from 130, you get 60, that's there. And then you do that. Of course, you're going to do the same thing. Okay. So if it happened that the lowest number was here, we would have used the number that was here rather to do the minuses. It just happened that in this case, all of them are under Atlanta. I think this one is clear. Now, once you've done this, this is what we call row reduction. Okay, row reduction. I mean, I wish that we'll be doing it together because sometimes when you're doing it together, you can appreciate it more. Now, you do column reduction. Column reduction. So when you look at this column, what is the smallest number here? What is the smallest number? It's 15. Okay. So when you subtract 15 from itself, you get what? 0. When you subtract 15 from 70, what do you get? 15 from 70, you get 55, and that's this here. When you subtract 15 from 30, what do you get? You get 15, that's this. And when you subtract 15 from 120, you get 105. Okay. Then you come here. As for this, we know. Okay, 0. So when you subtract 35 from itself, okay, you get 0. That's this. When you subtract 35 from 40, you get 5. That's it here. And when you subtract 35 from 60, you get 25, 35 from that. Okay. And then you do the same thing. The smallest one here is 55. Subtract it from every one of it, including itself. This is called column reduction. So you do the row reduction, and then you do your column reduction. That's why I said that it might look quite complex when you're looking at the procedure, the algorithms, but when you start applying them, it's not that complex. Once you're done with this, you cross out all zeros. So the first thing is that there are zeros here. You cross it out. and there are the zeros there. Okay, you cross it out, and then there are some zeros there. But the key point is you cross out all zeros, right? Anywhere that has got a zero. Okay, so anywhere with a zero. So if you look at this here, the zeros are here, it has to go. The zeros are here, it has to go. The zeros are there, it has to go. Once you cross out all zeros, okay, that will break things down for you. We had 3 lines in our case, if you check. This is line 1, line 2, line 3. So we had 3 lines, which is not a unique assignment. And the reason is because there are 4 rows or 4 columns. And so we need 4 lines, and that's the minimum. But we have, so because of that, we are going to subtract the minimum on cross value. The minimum on cross value. So when you look at these, okay, the ones that have not been crossed, okay, which ones are the minimum? 15, the minimum on cross value. We are going to subtract that minimum on cross value from all other on cross values that are bigger than the minimum on cross values. So you take this one, 15, you're going to subtract it from all of these. Okay. So in our next level, okay, and then of course we are going to add them to the values where the 2 lines cross. Okay, the values where the 2 lines also cross are these. So they cross here and they cross here. They don't cross anywhere else. Okay, so we add the 15 to them and then subtract it from them. So when you do that, okay, you're going to have this. You're going to subtract 15 from here. This will be 0. The one on the top right will be 0. Okay, this one will be 90 because you have 105 minus 15, and then the rest you all that. And then you add a 15 to this. This is what you get. Okay, so the optimal solution of the assignment problem has now been reached. Okay, do you sense that? Oops. Okay, I like the way this thing is done. Okay, so now we have 4 lines, or 4 unique assignments can be made. Now, how do we know that? Well, you can see zeros are here. If you have to get zeros, you get this from here. If you have to get zeros, you get this from here. If you have to get zeros, you get this from here. If you have to get zeros, you get this from here. If you have to get it, you can get zeros. You can have, you know, some percent. So once we have this, we are sorted. This is the final arbiter. So at this stage, wherever there is 0, okay, wherever there is 0, then we have to assign there. That is what it means. So if you pick somebody like A, officials in A, and we want to assign them, we'll assign them to where there is 0 now. And so we'll assign them to Atlanta in this section. Okay, we'll assign them to that. And then we'll assign those from B to Raleigh. And then we'll assign those from C to Durham. And then we'll assign those from D to Clemson. And that's it. Team A can now be assigned to Atlanta or Clemson. We know that, okay, but with Team A, we send them to Atlanta with a distance of 90. Now, if somebody says that we should assign them to Clemson because Clemson is 0 here, okay, the best you want to do is to come to the original, okay, and this is original. And you will see the distance between Atlanta and then Clemson. You see that the distance for Atlanta is shorter. The same way, let's go up. The same way when you go to this last one, even the B, okay, the battle is between this one and this one. Of course, we can't assign to one. So the B, as for the B, it's ruled out totally from Atlanta because you have this here. Now, the D is interesting. The D has the option of being assigned to Raleigh or being assigned to Clemson. Okay. And again, when you come back here, you will even see the guide, Raleigh on that. Now, somebody will say that the best is for him to go to Raleigh, but Raleigh has been assigned. Okay. And so that is why this becomes the final option for it. Okay. So team A can be assigned to Atlanta or Clemson, but then it goes to Atlanta, B, Raleigh, C, Durham, and then finally. So the goal is to get the minimum distance. And finally, this becomes the minimum distance that we have. Okay, that's the optimal solution. Okay. Sometimes you can have multiple optimal solutions. Okay, like that. And this is another multiple optimal solution. Okay, if we choose to sign A to Clemson instead of Atlanta, and team B to Atlanta, and then C to Durham, and then D to Raleigh, that will get the same total distance. And so we have this optimal solution. And optimal solution is good because you have a choice. It's okay. Okay. In an unbalanced assignment model where the total demand exceeds the total supply, you add a dummy variable to it in the table and you work it out. Okay. I won't bore you much with that here. And so this is your final network assignment. Okay. A goes to Atlanta, B goes to Raleigh, and everybody is happy with a total distance, minimum distance of 450. Ladies and gentlemen, that brings us to the end